Volumes of revolution. So what we're going to look at here, I don't know if you like highlighting your notes. I like highlighting. Solid of revolution is you take something and you rotate it around the x-axis, and that'll turn it into a volume. So let's do some coloring here. Let's look at our first picture here. What we have is some function. If we look at that green line, and we would say that that is a function, kind of looks like 1 over x maybe, or maybe part of a parabola. I'm not quite sure exactly what that graph is. But then if you took every single point on that graph, it has a y value. And that y value is exactly the length of that red line. Now, if I took that red line and I rotated it 360 degrees around the x-axis, let's use red crayon. Can you see if I took that one red line, I maybe shouldn't use red crayon with a red line, but I'll make the red line a black line. Perfect. If I took that one black line and rotated it 360 degrees, can you see that I would make a circle? Okay? And so there we have one circle by rotating one black line all the way around. Now this is going to build on a similar idea that you've seen before with volumes, right? And I'm going to go back to, because it's dealing with circles, I'm going to draw this shape. Maybe this should be dotted lines to look even prettier. Whoa, that's a crayon line. Here we go. That's a cylinder. A cylinder is a bunch of circles stacked on top of each other. The volume for a cylinder says, take your circle, pi r squared, and times it by the height, because here we have our one circle on the bottom. And if we keep stacking those circles up, then we would get the volume. What we're going to do is a similar idea here, is we're going to say, well, I have my one line, I rotate it around, that gives me one circle. Another place, if I take this point on my graph, that gives me another line for y. If I rotated that around 360 degrees, I would get another little circle. And if I put all of those circles together, that would fill in this whole shape and give me a volume. So how do we do that? Well, what is the area of a circle? Area of a circle is pi r squared. What is each of our radiuses? Our radiuses are all changing, right? Our radiuses are basically what f of x is. So then this becomes pi of f of x squared. Each of our radiuses is, in a sense, a tiny, like, remember when we're doing area under a curve? Like if I make a little rectangle, that would be an area under a curve there. If I kept making that area smaller and smaller and smaller and smaller, it would eventually approach my radius. How do we find an area under a curve? We find an area under a curve with an integral. And so then if we wanted to find our volume, we're going to integrate between two values and put in our function with pi r squared, with our function being our radius. And that will calculate all of those areas. And as it's going along, we'll calculate our volume. Now we've seen some interesting connections between area and volume already. We know that if we took, when we did our volume of our sphere, right, 4/3 pi r cubed, and we took the derivative, it became our surface area formula. And so now if we take an area, which is pi r squared is the area of one circle, and then integrate backwards, then that becomes our volume. So it's a really cool application, and what we're going to see within it is that we can figure out all sorts of volumes of all sorts of different shapes. For example, if we take these two curves right there, and you took one and you subtracted the other one, you would get this blue area. Then if you took that and rotated it around the x-axis, we should color it all in. Looks like this color. Oh, I love coloring. What shape would that be? What would you call that? Does it ring a bell? Okay. But it's pretty neat. Yeah, you might as well go home now, right? Yes. It looks like a bell. It's pretty cool that we'll be able to take two simple functions, and then because of the symmetry of the object, we'll be able to figure out its volume from that.